Hey everyone! So today, we're diving into something we do all the time without even thinking about it, turning things into percentages. But what if I told you that this simple act, this thing we do to make data neat and tidy, is actually hiding the most important part of the story?
I mean, you see it everywhere, right? Election results, market share, scientific studies. We just love normalizing everything to a clean 100%. It feels so simple and, correct. But this entire explainer is built on a really provocative question. What if by focusing only on the percentages, we're literally throwing away the most critical piece of information?
To really get our heads around this, we're going to need a completely new mental model. So I want you to stop thinking about probability as a pie chart. And instead, let's start thinking about it as a wave. Yep, a wave with some very specific, very important properties.
So what does that actually mean, to say a distribution is a wave? Well, it means that just like a wave in the ocean, a probability distribution has two totally distinct properties. And the big secret here, the part we almost always ignore, is that you absolutely need both of them to understand what's really going on.
Okay, first up, you've got what's called the amplitude. This is the how much. It's the total size of the thing you're studying, the total mass of evidence you have, or just the raw intensity of a signal. Think of it as the raw numbers, the absolute scale, before we slice it up into a percentage.
And then, part two, you have the phase. This is the what shape. It's the relative pattern, the proportions inside the distribution. Now, this should look familiar. This is your comfort zone. This is your classic pie chart, your 100% view, your normalized probability.
And this is where the rubber really meets the road. Just take a look at this. In ecology, the amplitude, the how much, is the total number of animals. The phase, the what shape, is the percentage of them that are, say, blue versus red. In statistics, the amplitude is the total weight of all the evidence you've gathered, while the phase is your normalized belief, like a p-value. In field after field, we're trained to only look at that column on the right, the phase. But the whole point here is that we're losing half the story by completely ignoring the left.
So that leads to the million-dollar question, right? If these two things, amplitude and phase, are so important, when is it actually okay to just toss one of them out? When can we safely just look at the percentages and know for sure that we're not missing something absolutely vital? Well, believe it or not, the answer comes from physics, specifically from how waves behave. To figure out if we can ignore the amplitude, we need to run what this research calls the dispersion test.
It all comes down to the medium the wave is traveling through. On the left, we have a linear or non-dispersive system. A great example is a beam of light in a vacuum. Making the beam brighter, upping its amplitude, doesn't change how it behaves. But on the right, you have a nonlinear or dispersive system, like waves in water. A massive tsunami behaves completely differently than a tiny ripple, right? The amplitude, the size, fundamentally changes the behavior of the wave's shape. That's dispersion.
And here is the absolute bottom line. Turning your data into percentages, or normalizing, is only safe and sound when the system you are studying is non-dispersive. It's only okay when the total amount of stuff doesn't change the internal dynamics of that stuff over time. And for all you math folks out there, here's the formal way of saying it. This quote is basically the mathematical version of our water wave analogy. It's just asking a simple question. Does the way the shape changes over time, that's dp by dt, depend on the total size, r? If the answer is yes, you've got dispersion. And if you have dispersion, normalization is actively hiding the truth from you.
All right, theory is cool and all, but where does this stuff actually matter? Let's take this dispersion test and apply it to a few real-world statistical models and see what breaks. This table just lays it all out so clearly. Check out the top two rows. Things like Bayesian updating, where you're just updating your beliefs with new data, they pass the test. They're non-dispersive, so yeah, turning your beliefs into percentages is totally safe. But now, look at the bottom. Population growth, mass-dependent killing. These are systems where everything is interacting with everything else. The total size, the amplitude, drastically changes the outcome. These systems are dispersive, and normalizing the data is a huge mistake.
So why does something like Bayesian updating get a pass? Well, it's because new evidence acts like a clean, linear filter. It might change the shape of your belief, sure, but the strength of your old belief doesn't change how the new evidence gets incorporated. The amplitude and the phase are totally separate. They're decoupled.
But then you look at population growth. Why does it fail so hard? It's all about self-interaction. A really dense population, that's high amplitude, is going to evolve in a completely different way than a sparse one. The size of the population directly messes with the relative growth rates. The wave is literally changing the water it's traveling through.
And you know what? Here's the real kicker. Ecologists already know this. They would never ever just track the percentage of different animals in a population. No way. They always track two things: the total population size, our amplitude, and the distribution of traits within it, our phase. They've been avoiding this normalization trap intuitively the whole time, and now this framework finally gives a solid reason why.
Okay, let's zoom out for a second. What's the really big picture here? What does all this mean for how we should be looking at data from any complex system?
I mean, this whole thing opens up a massive question, doesn't it? If our standard way of doing things, our classical probability, only really works for these simple, non-dispersive systems, what are we supposed to do for everything else?
The solution, you'll be happy to hear, isn't actually that complicated. It's profound, but it's simple. We just have to stop throwing information away. We need to use what the research calls an enriched state space, which is just a fancy way of saying we need a model that always tracks both things: the shape, our phase, and the size, our amplitude.
And this leads us to what might be the most powerful, mind-bending idea in this entire explainer. The source puts it perfectly. Classical probability theory corresponds to the non-dispersive regime of stochastic dynamics. Think about that. Probability as we know it isn't the whole story. It's just a special case. It's the easy mode that only works when things are simple and linear.
And so, I'll leave you with this final thought. Classical probability works great for linear systems. But how many of the world's truly complex systems, the ones we really care about, like economies, ecosystems, societies, are ever actually that simple? So the next time you see a stat presented as a neat and tidy percentage, just ask yourself, what was the amplitude? What was the raw power, the total size that got erased to tell me this clean little story?